Hello everybody. As you know, I'm on travel, but I didn't want to leave you in the lurch because you've got some logic to do. So what I'm doing now is I'm going to record a couple of lectures for you so you're up to speed and you don't get lost, especially as you're doing the homework and preparing for the next exam. So I'm going to walk through slowly the resources that you need to do well. Hopefully this will be as engaging as it typically is when I'm in the classroom, although we all know video is a poor substitute, but I'll do my best. So first let me remind you of our language. And where we left off is I was introducing, we sort of gestured at the introduction of a new language, a kind of an expansion of the language we've been playing with in the course so far, which we're now labeling L1, language 1. I want to remind you of both of those. So language 1, if you recall, just syntactically, it's a set, consists of a set of our connectives, disjunction, conjunction, material conditional, negation, as well as parentheses, so we can group things together, and then P's, Q's, R's, etc. And that's it. Of course, we have some what we call semantics associated with it. And one has truth tables. The truth tables we use to define the connectives. The truth tables, I'll write that out, define semantics for our logical connectives for L1. And just to make it crystal clear, when I say logical connectives, I'm talking about these logical connectives. And so that's the disjunction, conjunction, material conditional, as well as the negation. So those are our logical connectives. And the truth tables give us the semantics. They define the semantics for them. Basically, what do those expressions mean, or what do those connectives mean? And then otherwise, we kind of leave open, the meanings of P, Q, R. Those are declarative sentences. They're truth apt, but we kind of leave open what exactly they mean. We're mostly, almost entirely interested in the connectives in this language. They're really highlighted, and the semantics associated with it. Of course, now where we're headed is we're going to also define proof theory for L1, and the proof theory is connected to the semantics. And we've already seen some of what this proof theory entails, or might entail. It's a way in which that we attempt to capture consequence in this language. So consequence being what follows from what. And we've talked about these sentences like P, Q, R, etc., that they're representing being truth apt. And the consequence that the what following from what that we want to preserve in our proof theory is truth. So we're trying to preserve truth from premises, we'll say, to conclusions. And what we're going to do is construct proof rules that allow us to ensure that whenever we're moving from premises to the conclusion, or to some conclusion, that we're preserving truth. And again, we've seen some of these. I've kind of gestured at them. We'll talk a bit more about them today. But they're things that kind of govern the use of the connectives. So we've given them names like conjunction, introduction. We'll abbreviate that CE. And it looks something like this. Whenever you have P, whenever you have Q, you can introduce a conjunction, P and Q, right? So proof theory, the proof theory is going to consist of moves like this. And the claim in this language is that for our given proof theory, anytime you have true premises, you get a true conclusion. And that is, if you recall, there's a special word associated with structures or arguments, we'll say, that look like this, that follow this proof theoretical construct. These rules, they are valid. And so validity, just to remind you, are about arguments. Arguments are valid just in case. That is to say, they're defined, the validity is defined in these terms. If the premises of a given argument are true, then the conclusion must be true. Validity. So that's what valid means. If the premises are true, then the conclusion must be true. And you can see that very clearly with conjunction introduction. If it is true that P and it is true that Q, then it better be true that P and Q. all of the proof theory rules that we construct in this language preserve truth in just that way. They're valid. Just so you have that table in mind as well. I'll put it right here. Hopefully you can see that. That's not a great marker. Pick another one. Something maybe a little easier to see. Perhaps I'll just stick with this. Nope, that one's bad too. Don't know why I changed. All right. So I'm going to draw this circle here. This is kind of what you need to remember when you're thinking about validity. You have that whole space of arguments. A proper subset of those are valid arguments. And then a proper subset of those are sound arguments. And sound arguments are valid arguments that have true premises. Soundness is the thing that philosophers are typically after. Like, they want valid arguments, but they want valid arguments with true premises. We're going to stick kind of in the aether a bit and just think about validity. Often that's hard enough, right? But just so you see that contrast, though, there's sound arguments, there's a subset of the valid arguments. And you can think of validity and soundness as two ways to be good. Like, valid arguments are good arguments in some sense, insofar as the premises entail the conclusion. But you really want better than that. But of course, there are a whole slew of arguments that are not valid, have no connection between the premises or conclusions, or perhaps like a tangential or incidental relationship between the premises and conclusion. Those are not valid arguments. They're also not sound arguments. So, because if your argument's not valid, it can't be sound. So just remember these subset relationships. That'll help keep you, beaded appropriately on validity and our focus here, especially as we again think through fleshing out the ways in which we can move symbols around and like with something of a little proof theoretic calculus in a way that allows us to preserve truth from premises to conclusions, in a way that allows us to respect the semantics defined by truth tables, all within this rather small language. So far that should just be a refresher. Just kind of want to beat that drum a couple of times. I'm going to pick up on the L1 proof theory as later on today. But before I get over there, I do want to pick up on this other topic that we're discussing. It's kind of the limitations of L1. So as I said, we don't really get into, the nuances of P's and Q's and R's. We're just in this language focused on the connectives, like defining semantics for the connectives, ultimately defining a proof theory for the connectives. But, that only goes so far, especially if you're trying to represent something like natural language. And we want these languages that we construct to line up as best as we can to natural language. Natural language, I'm talking English in this case, it's a beast, right? Like, natural language is kind of messy. It'd be super surprising if you could capture, natural language in English was just focused on connectives like this. The language, I think, would be much less interesting. But let me show you a little bit about what we can do, or remind you about what we can do with this language, and then show that'll kind of highlight what we can't do so well. So some things that we've discussed as kind of a recipe form that we can do is you can pretty easily, in a lot of cases, translate conjunctions. So John is happy and John is bald. You just introduce, P for John is happy, introduce Q for John is bald. The conjunction's right there, and then you go P and Q. Now, in natural language, we don't always work this way, like and doesn't always work this way. So John went to the store and John bought milk. There's a plausible reading of that where it's a connection. Like, John wouldn't have gotten milk if he didn't go to the store. Another way of saying this, plausibly, is if John goes to the store, then John buys milk, right? So sometimes and can be read in that kind of causal or conditional sense. You just have to keep an eye on that as a natural language speaker when you're doing translations from natural language into this language, L1 or any of the other languages that we work on. So that shouldn't be too challenging. There are some that are a little more challenging, but also some recipes or some natural language expressions that are a little more challenging to put in here, but also some recipes that I can give you to make it a little easier to understand. And so here's one. So we sometimes in in our language, sometimes in natural language, we'll say things like neither nor. Like, I neither want this or I neither want that. You know, John, I'll say Mira, because my daughter Mira says things like this. Mira wants neither vegetables nor eggs. Now, she doesn't exactly say this, right? She's only 4, but sometimes she will say things very close to neither wanting vegetables nor eggs. And so what we want to do is we want to think about, like, how would we represent this in our language, and just using connectives and P's and Q's. Now, clearly there's negation involved, right? And so what we want to say is, we want to capture, like, first of all, try to identify what the P's and Q's are, right? So we'll say Mira wants vegetables. We'll say this is P. Mira wants eggs. We'll say that's Q. All right, let's think this through. So now what we're trying to get at is that of the options, she wants neither of them, right? And that's different from saying, like, you know, not wanting both of them. It's plausible. So a kind of a recipe you can think of is, like, treat that neither as like sitting outside of the options, in a sense. She wants neither of these things. In the sense that, like, if I were to put P or Q as options, I want to find a way to put the not on the outside of them. So Mira neither wants P or Q. It's not the case that she wants P or Q. It's not the case that she wants vegetables or eggs. Neither nor. This is different from saying something like, Mira does not want both vegetables and eggs. And we can use our same key here, P and Q. But we're saying, like, we're sort of leaving an option open here that she might want one or the other, but not both. She doesn't want to eat vegetables and eggs together. She doesn't like omelets, I guess. And so we can capture that too by thinking of negation on the outside. So negation, we got our P and our Q there, and then we use conjunction, right? So it's not the case that she wants both vegetables and eggs. She might want veggies, she might want eggs, just not together. So the important part here, so when you're thinking, when you see neither nor, and you see not both, we have some recipes that you can use to translate these into our L1. So neither nor is not P or Q, not both is not P and Q. And so if keep that in mind as you see these expressions in natural language. Just check yourself. Is that appropriately translated based on our understanding of truth tables for negation, truth tables for disjunction, truth tables for conjunction? You'll start to see, if you've got this heuristic in mind, there's a kind of a clear translation across these, and you can use this as a heuristic. So you don't have to think very hard when you're doing the translation. It's kind of a recipe. I don't want you to get tripped up on these, so keep the recipe in mind. Now, there are some that are a little more complicated, and also, because of the way natural language is, more prominent. One that typically trips up students is the use of unless. So unless is a plausible interpretation in this little language. In natural language, though, it can feel a little messy, so I could say something like, unless John goes to the store, he will buy milk. So now, how would we translate that in our logical language? So I want you to, pause the video for a second. Think about this. How would you handle this? But after you've thought through it, or perhaps read the book, just remember this recipe because this one's actually very tricky. People typically get this or trip this up or with other expressions or get rather complicated. There's actually a pretty straightforward way to understand this expression. And there are two, and I'll highlight both. One involves negation. It's kind of closer, I think, to the natural language. The other is sort of, it's logically equivalent to the one that involves negation, but it's easier to understand from the language perspective. So what I'm going to do again is I'm going to show you the one, like an interpretation in our L1 that looks rather close to kind of the natural languagey representation of this sentence. And then I'm going to show you one in L1 that kind of looks close, or looks a bit closer to the L1 language itself. And so there's like, a bit of intuition mongering on this, but hopefully you'll be able to see both. And so unless, just as a rule of thumb, you can treat as if not, or if not, or not if, that is. So when you see unless, you can treat it as not something that precedes a material conditional. So if not. So if I have John goes to the store as P, I'll say John buys milk as M. Unless John goes to the store, John will buy milk. If not P, then M. Another way of putting that is John doesn't go to the store, then he'll buy milk, which is logically equivalent to saying just this simple expression, John goes to the store or John buys milk. Now, we've seen an equivalency between expressions like this so far. Just generally, if P or not, P then Q, and then logically equivalent to not P or Q. So you've seen that before. You also know that whenever we have not on something, it's equivalent to that thing itself. So if you put all this together, you'll be able to see that these two are equivalent. So not P then M, P or M. Now, if you don't believe me, if you're still like, I'm not sure, John, you know what we do. Anytime you say this, truth table. Because that's how we determine the semantics for the language. So write truth tables. Right, two truth tables, you'll see that they have the same truth value in every case. And what does that mean? They're logically equivalent. So, and if you're not, I don't trust that you're actually going to do that. So for the rest of you, just take my word for it, unless, if not, or not if, that is. Now the other one that's kind of tricky for folks is otherwise. Otherwise, natural language, we see this all the time. John goes to the store, then John buys milk. Otherwise, John buys candy. John goes to the store. John goes to the store, and John buys milk. Otherwise, he buys candy. Now, pause for a second, think this through, and then I'll give you the recipe for that, and then we'll move on to some limit cases. But I'm assuming you're paused. Now the first one here, John goes to the store, P, John buys milk, Q. We'll go ahead and give an R for the candy. So we have 3 sentence letters here. We should be pretty straightforward how we capture if John goes to the store, then John buys milk, right? Just if P then Q. We want to say something in addition. It's the otherwise. What is otherwise doing, right? We're giving some other information. We're saying something, he'll buy candy instead. Put a conjunction here. If John goes to the store, then he buys milk. And it's the case, here's our additional information. Otherwise, that is, if he doesn't go to the store, then he buys candy. So, the recipe here, you have something like if P then Q, and for otherwise, not P, then something else. That's how otherwise works. Otherwise is, in a sense, negating the first part, the thing that the arrow is pointing from in a conditional, and basically fleshing out the space of options, right? If he does do this, this is going to happen. But if he doesn't do this, this other thing's going to happen. That's otherwise in a nutshell. So, give you some recipes there. You'll see more of this and get some practice of this in the hard degree textbooks. I encourage you to go check that out. But that is in a nutshell like the basis, I think. Really all the tricky cases you need to know with associated recipes for this course when you're translating from L1 into natural language. Now, there are plenty of other tricky cases. We've talked about some of these. I do want to highlight just one in particular that's kind of motivated some of our thinking, especially as we move into other languages, and we'll continue to do so. So my favorite example of this is John and Sally are married. So right now, given L1, all we have is a way to represent the sentences that are conjoined, right? John is married. Sally is married. So if we say that's P, say this is Q. Essentially, the best we can do, or one plausible read of this is that P and Q. John is married and Sally is married, but that's not really capturing the expression. That's not really capturing what we're intending to convey by John and Sally are married. What we're trying to say is that they're married together. They're married with each other. They're related, or in that way. Married is a relationship, right? And so far, we just have P's and Q's that kind of hang out on their own, and we don't really have a way to bridge that connection, like, right? So this is actually, P and Q, John is married and Sally is married. It's in a sense not enough information to really reflect the sentence that we intended to convey. Another way of representing this is just by a sentence letter. Like they're married, like John is married, or John and Sally are married, because at least that's not saying anything, allowing for anything false, right? Like at least there's the connection here. It's just that we can't unpack it with our language. But here we've sort of unpacked an entailment of this expression, but then we've lost, like the what's true, the other aspects that are true, that they're related or that they're married together. So while this would follow or should follow from this, it doesn't capture everything. At least in this case, we haven't, we aren't allowing other interpretations. There's just one interpretation of this expression. It's just that we can't unpack it with our language. And so again, just to reiterate that, we could represent John is married and Sally is married, like this P and Q. That is something that would follow from John and Sally are married, but it doesn't capture the relationship they have together. And it allows, in fact, interpretations where John is married to someone else and Sally is married to someone else, and we don't want to allow for that. We're trying to represent as closely as possible the meaning of the language here. To my mind, the best thing we can do then is to just, given the limitations of this language, have a sentence letter represent that sentence, because at least we're not allowing for different interpretations. Now, one of the benefits here is you can break apart John is married, Sally is married. Again, consequence, what it follows from this. You can't really break R apart. There's nothing to break apart. We only know how to break apart things like conjunctions, disjunctions, material conditionals, and negations. So it's a limitation of the language. Now, one thing, this kind of spurred the development of more sophisticated languages that kind of get into the grammar more of natural language. And so with that, I just want to point you to a language that we're going to be building on. We're going to focus too much on it now, but I do want to, prime you, and that's what we'll call L2. And in L2 you have L1 plus, you also have what we call predicates and objects. So predicates are they're going to look like our sentence letters, but they're going to be slightly different insofar as they have slots in which you can fit individuals or objects. And so they're going to come in, they're going to have, what we call different arities. And that is, that arity just means the number of slots you have available. So you can have like a sentence letter that represents a predicate like pretty, or a sentence like P, or a sentence letter that represents red and has one slot. So, and what this is like pretty is a predicate, it's a property, and we can slot in different things as being pretty. Red is a property, and you can slot in different things as being red. It has both of these examples have an arity of 1, that is, they can take one individual / object. But you can also introduce predicates that have different arities, like 2, 3, and so on. In fact, if we want to capture that marriage case, we'll need a predicate that allows for at least 2 slots, right? So we can just do that here. M, 2 slots, and we can define this as married. And what this does is it relates one individual to another individual, saying that they're married. We can go forth and go on. My favorite example of a ternary or a 3-place predicate is between. So something's between 2 other things. You need three individuals, or 3 slots for individuals in that. And then this, you can go on and on and on and on. But well, I suppose that's not the complete language. You can go on and on with the arities. You can go on and on with the predicates. In addition, what we have are what you can think of as names for the individuals. So A, we do that with lowercase a, b, c, and so forth. So like this could be Alex, this could be Bob, this could be, Chris, like ABC, just names for things that might go in to these slots here. So if I want to represent what I had, John and Sally are married, I do this here using L2. It says there's this predicate. Another way you might describe it is a relation. It's 2-place, and it relates John, and it relates Sally. And I'll just drop these slots off. But that's it. John and Sally are married. The relationship holds between them, right? Marriage is a relationship that holds between John and Sally. You can do this with other expressions, right? So John is happy. John is happy. This one, happiness plausibly just has 1 slot, so I can just use H to represent that. It takes one object, and there's John. John is happy. And so hopefully you can see how this is a way in which we can get a little more into the grammar of natural language, at least in English, grammars that have predicate and object relationships. Many languages do. This is how we can formally represent this information. And so it should follow from this sort of thing, John and Sally are married, that there might be a 1-place relationship, like a property of being married. It should follow from expressions like John and Sally are married, that John is married and Sally is married. So that way we can capture that that kind of L1 representation of this expression that was not exactly adequate to represent the semantics of natural language. We can still get the right entailments, and we would expect this to follow from John, that relationship between John and Sally. So we're going to spend a bit more time on L2. Again, I'm just kind of whetting your appetite, as it were. I want you to get a little taste for that and see some of the limitations of this, of L1 and its focus on connectives, and how it may or may not line up exactly with natural language. And so for the rest of today, though, I would like to focus on, and I'm going to hit back up on that proof theory stuff I was talking about. So the proof theory, again, so proof theory is going to be for L1. So again, even though I just talked a bit about L2, I'm going to shift gears now. I'm going to go back to L1. We're going to spend more time on that. We'll hit L2 eventually. For L1, again, we have the semantics, which is the truth tables. And that tells us what these connectives mean. It tells us how we preserve truth, so like what truth values, how we can assess expressions in a language in terms of their truth or falsity. And now what we want to do, though, is bridge this language and its semantics over to argumentation, so validity. And what we're on the hunt for. What we kind of on the hunt for here is like we need proof rules or proof theory rules, like ways to generate proofs that respect the semantics of the truth tables, just using this limited vocabulary. And we've kind of been talking about that a bit. We talked about like conjunction elimination, conjunction introduction, etc. I've been kind of intuition mongering you about, aren't these good arguments? Are these good arguments? Are these bad arguments, right? Bad and good being cashed out in terms of validity ultimately, and perhaps soundness if you're a philosopher. But here, like we want to like focus in on what exactly those rules are, so that we can use them in combination with other rules to generate truth-preserving arguments for surprising conclusions. That's kind of what we're interested in. I want surprises. I like to be surprised. So again, we've seen a lot of what of these proof rules already, but it's worth writing them out. Conjunction elimination. This is CE, and this is 1, P, and Q. You can infer P or Q. Conjunction elimination. It has a pair conjunction introduction, which I'd written up earlier. P, Q. You can infer P and Q, and this is abbreviated. Oops, this should be, yeah, no, I got that right. CI. This is kind of nomenclature we'll stick with. Eventually, you're going to be using these to justify moves and proofs, and so we're going to give them a little abbreviations. So CI for conjunction introduction, CE for conjunction elimination. We also have disjunction elimination. This is where you have a disjunction. We need a proof rule that preserves like truth that allows us to get rid of that disjunction. And so disjunction elimination, DE. So if you have P or Q and you have not Q, you can infer P. Of course, if you have P or Q and you have not P, you can infer Q. So if you can negate one of the sides of the disjunct, you can infer the other. And that's the heart of disjunction elimination. There's also disjunction introduction. That's DI. And this works just like if you have a P or Q or whatever, you can always just introduce disjunction. So if P is true, then P or Q is true. If Q is true, then Q or S is true, right? Like you always just introduce a disjunction. So these are 4 of our rules. There's some more. Again, I'm going to write these up painstakingly, as it were. These are kind of the basis of our proof theory. And again, you've seen them before. It's worth just like repeating them kind of over and over again into the kind of in your background knowledge, because you're going to be using them a lot to make moves, valid moves from sets of premises to conclusions while we're proving things. So there's also negation, introduction, and this is just you have P or Q or S. You can always tack on 2 negations to the front of it. Why? Because if not P is true, then P is true. If P is true, then not P is I'm sorry. If not P is true, then P is false. If P is true, then not P is false. So it's like a light switch, flip on and off. So if you iterate that one more time, you know if P is true, then not P better be true, because not P was false. You can do the other direction. So negation, elimination. Let's see, this is NI, and this is NE. And this just says if you have not P or not Q or not whatever, you can just drop those 2 knots off. And then strip it down. You can always drop off or add negations in pairs, basically. There is also, we have conditional elimination. Call this CE. This is also sometimes known as modus ponens. You have if P then Q. You have P you can infer Q. So if P then Q is true, and P is also true, then Q follows. That's conditional elimination. Now, for reasons that will become clear, there's not a rule of this simplistic sort that allows us to introduce a conditional. So there's a simple rule that allows us to remove a conditional. There's not a simple rule that allows us to add a conditional. And we'll see that as we move forward. But what I've described here, these simple rules, there's 7 of them. They are what we call, well, let's see, I want to use a different marker for a dramatic effect. You guys know I love drama. These are direct derivation rules. And what this means is just like these rules, simple inference. Like you do it in your head. You do it without thinking of it. If P is true, not P is true. Just a quick step. If P and Q are true, P is true. If P or Q is true and not P is true, then Q is true. Like, not a lot of complicated reasoning there. If P then Q is true and P is true, you know Q is true. You don't really have to think very hard. They're direct. You just move from the premises directly to the conclusion. We're gonna talk about 2 other types of rules. We really call them methods. In fact, let me show you. So direct derivation methods. We also have what we'll talk about conditional derivation method, and that's how we introduce conditionals into our conclusions. And we also have an indirect derivation method, which is the biggest one. It's the most powerful one, and you'll see more. It's probably going to look really creative, but it's essentially you assume the thing you're trying to prove is false, and you get a contradiction. No, we'll get there. Right now, again, focus just on direct derivation methods, and this is good because you can kind of combine all of these methods together to prove some interesting things. It's good to get the base case, the kind of easier case down. We're just doing proofs that have these rules associated with them, or that you can derive things just using these rules, and you can derive quite a bit just using the direct derivation rules. So let me show you. So hopefully you were writing some of that down. But I'm going to give you a bit of a format. Again, a recipe. I'm big on recipes for walking through proofs. So I will give you questions that look like something like this. P, let's see, Q or R. If P, then not Q. And then I will say on line 4, show R. And this will be the setup for a proof. Hopefully, can you see that? Yeah, maybe, let me see if I can write. That's a little easier to see. Now you can't see the top. That's okay. You don't need to. Okay. So you see here's P. If I make that a little brighter. This is important enough to belabor because you're going to see this a lot. I want you to know what to expect and know what to do when you see it. And so I'm going to give you proof setup, like problems that look very similar to this. They're always going to have this sort of format. I'm going to give you premises. Premises. And here are going to be the premises. So in this case, 1 through 3. Premises. And then I'm going to say, show me this conclusion follows. So I want you to prove using our rules that R follows from P, Q or R, if P then not Q. Let me walk through this and show you how you can do this. And so, all right, here's how you should think about it. You're just like, okay, I need to show R. You can work backwards, you can work forwards, whatever floats your boat. You should be thinking, okay, looking through, finding R. Okay, there's R. Cool. R is embedded in Q or R. So you can't just pull R out. It's in this expression, this complicated expression. You need to figure out a way how to break it out. And so you see a disjunction. It's connected by disjunction to Q. You know how to eliminate disjunctions, right? If you have, and now I'm going to use, for reasons that we discussed hopefully in previous lecture if I remember to, I'm going to use the kind of Greek meta letters to describe this. If you have, phi or chi, and you have not phi, you can infer chi. And what is this? Disjunction, elimination, DE. Now, if I didn't cover the use of phi's and chi's, technically, the reason I'm doing this is because phi's and chi's are the variables that range over all the possible sentence letters. And so, strictly speaking, when I write P or Q, I am talking about a specific instance of sentence letters. Specific sentences like John is happy or John is bald. And so if I put not Q, and then not what I got up here, not P, and then infer Q from that, this isn't really a rule. This is an instance of a rule because that sentence is representing John is happy. That sentence is representing John is bald. So this whole inference is just about John and his relationship to baldness and happy. Strictly speaking, that's not a rule. It's not repeatable. It's just this one instance of a rule. So hopefully I talk about that before this lecture. But if not, this would be the actual rule itself representation. It's the pattern. It's the bigger pattern, right? You can plug in any P's and Q's in there. In any event, getting back to the thread, disjunction elimination, we see that. We've seen that rule. Now we